Hey everyone, what's up? I hope you're all doing well. So welcome to a new video, and today we'll be solving this question called search in a rotated sorted array. This is a medium level problem from Leetcode, and it's commonly being asked by Facebook and Amazon during the recent couple of hiring sprees. So let's quickly run through the description of the problem and then we'll move on to its explanation as well as the code. Alright, so the problem says that we are given an integer array nums which is sorted in ascending order and all the values are unique, and also an integer value target. So nums is rotated at some pivot point unknown to us beforehand. So for example, here this is the actual sorted array, and after rotation this becomes something like this. So these three values move to the end, and now if target is found in this array, rotated array, so we should return its index, otherwise we should simply return -1. For example, in this case the target is 0 and 0 is found at index 4, so we return 4. And in this case the target is 3, which is not present in this array, so we simply return -1. Similarly here 0 is not present in this array, so we should return -1. So that's pretty much it. We'll simply move on to its explanation and then we'll write the code. Alright, so let's move to the explanation part for this particular question. So here we are given a list of numbers and they are sorted and rotated. So you can clearly see that they are sorted from here to here and then they are rotated, and basically the rotation starts after 2, and from this point the array is rotated. So we need to find, we are given a target element and we need to find the index of that target element in this array. So the index currently is 4, as you can clearly see, and if it does not exist we need to return -1. But in this case, since it exists, we need to return 4 in this case. So how do we approach this? The first approach is obviously to go for something like a linear search, and you can simply search the entire array starting from the first element and until you find 0. As soon as you find 0, you can return its index. If you reach the last element and never find 0, you can return -1. And linear search, as we know, takes linear time. So this is going to be big of n in terms of time, and so this is the time, and we're not using any container or anything, so this is constant in terms of space. So this is the first solution. But then you can definitely do better, because they have already told you that the array is in a sorted format, and we never actually use this information in this solution. So whenever we come across an array being sorted, we can immediately go for binary search. But because this is rotated as well from this particular point, we can't really apply a normal version of binary search, so we'll have to make some modifications to control this particular rotation as well. So for binary search approach, I have again listed the number of elements once again, and if I draw these elements to visualize the approach, so if I plot these, so they are something like, let's say 4, 5, 6, 7, so they are linearly increasing, and then after 7 we have 0, 1 and 2, so it suddenly drops down to 0 and then it starts to increase again from 0 to 1 and 2. So this is the plot for this particular list of numbers, and using this plot we can analyze the logic of dividing our array into two parts, that is going either on the left half or the right half during binary search logic. So what we can do is, we start our binary search normally, so we'll have two indices, we'll have the low index and the high index. Currently we have low index to point to 0 and high index to point to the last index, which is 6. So the mid index will be 3 for the first case when we apply binary search, and at 3 we'll get the value 7. So for every new mid index of the binary search, the first thing we'll do is we'll check if our required value, our target is 0. So we'll check if mid index is 0 itself. So is 7 equal to 0? No. So mid index is not the current target value. Now we need to derive some logic to either decide if we want to go to the left half of 7 or the right half of 7. And we'll try to use this property that the array is rotated from this point in order to derive this logic. So what we'll do is, our target value is 0, right? Now, whenever we have a mid index, one thing is for sure. For example, currently this value 7 is the mid index where I'm at. So including my mid index, I must be either in the left half or the right half, including my mid index, and one of these halves will always be sorted for sure. So for example, in this case, since this mid is not included in my right half, it's currently in my left half, and I can clearly see that my left half here is sorted from 4 to 7. This part is sorted. But if I were to include this mid index for my right half, so from 7 to 2, this part of the array is not sorted. So one of these will always be sorted. Currently my left half is sorted. So using this logic, I can quickly check if my target element 0 belongs in my left half or not, because for all my elements in my sorted half, I can clearly compare the first one and the last one to check if 0 lies in this particular sorted half or not. So I'll just compare, is 0 greater than equal to 4 and less than equal to 7, which is not, because 0 is less than 4. Since this half is sorted and 0 does not belong in this half, I can clearly say it with surety that 0 will lie somewhere in this half. and this is how we are making the logic. So once we decide the 0 will lie in this half, we can simply update the low pointer to point to mid plus 1. So our mid was currently 3, and 3 plus 1 is 4. So the value of our new low index now is 4. So this will be the new low, and our high is still at 6. So we'll have the new mid index as 5. Now once we reach 5, index 5, we'll check the value at index 5 1. Is it equal to our target 0? No, it's not. Then we check if including our mid index, this left half is sorted or not. So we can clearly see that this is sorted because its low is less than or equal to its mid. Then we'll check if our target element 0 lies in this sorted half or not. So is target element lying between this range 0 and 1? Yes, it is. So we'll quickly shift our search to the left half, and the left half means our high will now be the current mid minus 1. So our mid is currently at 5, so this will be 5 minus 1, which is 4. So our high will also point at 4. So our low and high both point at 4 now. So our new mid will also point at 4 because it's low plus high over 2. So mid is also at index 4. We'll check the element at index 4 finally. Is it equal to our target 0? Yes, it is. So we have found the element, and this value 4, the index, is what we'll return. So this is our returning index. And in this case, since 0 is present, so we return the index 4. Had there been some other value instead of 0 here, so our search space would have exhausted by now. And if we still didn't find the target element, then we can simply return minus 1 as the answer to our function. So this is what we're doing in this particular question. So in this graph, in this plot, for example, we first checked if this half is sorted. Since it was, we found that the target element does not lie here. So we moved our search space to this half. And in this half, again, we broke it into two parts. We first saw if this is sorted, and since it was, and our target also lied here, we moved our search space to this half, and that's where we found our element. So what we're doing is essentially a simple binary search. At every point, we are dividing our array into two halves, and when we are dividing it into two, we already know that the time complexity for binary search is big O of log n, which is log to the base 2, since we are dividing it into two equal parts, and we are not using any extra space here, so the space complexity will be constant. So the optimal time and space for this question is log n time and constant space, and you can clearly see that this approach is much better than the linear time because log n logarithmic is much faster than linear. So this was the approach that we will go for using binary search, and now let's quickly move on to the code. Alright, so now that we are done with the explanation using binary search, let's quickly code it up. So we are given a function search which accepts a list of numbers called nums and a target value, and we are required to return an integer denoting the index where this target is found inside this nums list. So using binary search, we simply start with our low and high pointers. So I'll have my low pointer pointing at 0 and my high pointer pointing at the last index, which is nums.size -1, its last index. And now as long as I have values left in my array, so as long as low is less than high, we are still inside the array. What we'll do is we'll first find the mid index. So the mid index is simply given by low plus high minus low over 2. So the reason we are doing this high minus low is simply for avoiding any integer overflows. If this value becomes too large, then it might overflow, and high minus low, this particular operation keeps it within the integer range. So once we're done with this, the first step, as we discussed, was to check if our target lies at this mid index itself. So we can simply check if nums of mid, the current value at mid index, is same as the target that we want to find. If it is, then we found our current mid index that we want to return, so we can simply return mid from this function. Otherwise, if mid index is not the target, then we'll check if including mid, the left half is sorted, or otherwise if including mid, the right half is sorted, because we know at least one half is always going to be sorted. So let's just check for the left half. So if nums of low is less than or equal to nums of mid, so this means the left half is sorted. So let me just quickly comment this. This means that the left half is sorted. So now if the left half is sorted, then we can quickly check if our target element lies in this left half or not. And we'll check that using if target is greater than equal to the leftmost value of the left half, which is nums of low, and also target is within this range. So it's less than equal to nums of mid, which is the rightmost value of the left half. This means that target is in left half. And since target is in left half, we can simply move our binary search space to the left side of the array. So we can simply have our high pointer as mid -1, right? And otherwise, if this is not the case, then obviously target might be in the right half if it exists in the array. So we can have our low pointer move to the right half. So low goes to mid +1. Now this particular thing was the case when left half of the array is sorted. Otherwise, we can check if the right half is sorted, and we can simply mention it here as an else condition. So this would mean that right half is sorted. And now since we're talking about right half and we know that it's sorted, we can quickly check if our target lies in this right half or not. So I'll again do the same thing. If my target is more than the starting point of the right half, which is nums of mid, and if it's less than the ending point of the right half, which is nums of high, so this means the target is in right half, right? So we'll simply reduce our search space to the right half, and we can do that using low, making it point to mid plus 1. And otherwise, if this is not the case, then obviously the only possible condition is for our target to be in the left half. So we can reduce our search space to high pointing to mid minus 1. And I think that's pretty much it. Once we go out of this loop, that would mean that we have actually exhausted our entire search space. The entire array we have checked and we never really found the target. So we can simply return -1 from this case. Otherwise, this particular thing will return the correct mid index whenever we found it. So let me try to run this for a sample test case to see if this works. So it's working for a sample test case. Let me submit this to check if this is getting accepted. And it's faster than 100% of solutions. So the runtime is 0 milliseconds. So I think this is a pretty good solution. And complexity wise, binary search, it's logarithmic. So it's the fastest you can go for. Yep, so that was it for this video. If you liked it, do hit the like button and do share it with your friends. Also, if you haven't subscribed it, please subscribe for more such content. And yeah, thank you so much for watching, and I'll see you very soon in the next one.